So far, we have completed the first case. Let's go to the digital transmission. Well, this is not the example of the digital transmission. This is an analog transmission. The first transmission, the old-fashioned telephone or telegraph, that works in this way. We have a signal to be transmitted, maybe our voice. We need to transmit into a medium that, for example, is bandpass or has different properties, a radio channel, and so we need a modulator to transfer this at a higher frequency. And then the signal is attenuated by the medium and derive very, very, very small, and it's added by a lot of noise. It's corrupted by noise, we can amplify it, but what we get in the end is a signal plus noise. So this is what we transmit, and this is what we receive when we have some noise. But we have a lot of noise, then it's impossible to transmit. So there are many cases in which we have noise. For example, when our phone call traverses several centrals, and each of the central introduce a corruption to the signal, and so introduce noise, noise, and noise, in the end we understand nothing. Or when we have only one point-to-point transmission, but the distance is so far that the attenuation is huge, and we get nothing out of this. And this is why digital transmission helps, because digital transmission is a way to ideally remove the impact of noise. How we can do? Well, first of all, we take a signal, but we should convert this signal into a bit stream. This is done by a digital to analog conversion, and this is an example of how this signal can be represented into bit. Then we can decide to transmit each bit, that can be either 1 or 0, by a waveform. For example, we can choose a square waveform, amplitude 1 for a 0, amplitude -1 for bit 1, and so on and so forth. So this is another kind of waveform that is baseband, limited, band limited, and this is a waveform that a band limited modulated, so a bandpass waveform. And then what we do, as each bit is represented by a single waveform, and we are interested in its amplitude, either positive or negative, because this is a bit, we need a matched filter, as we already have seen in the past example, and then we have only to decide if out of the matched filter the signal is positive or negative. This is the decisor that do this. If it is positive, then we say the bit is 1. If it is negative, the bit is -1. Of course, we have a probability of error, because if the signal arrive theoretically negative, but the noise that has some probability distribution corrupts the signal, it can change its value and make the signal positive. And so the bit that was, for example, 0 becomes 1 due to the effect of the noise. But we can compute the probability that the noise exceeds the value of the signal, and this is the probability of error. Is again another Q function that is the tail of this Gaussian. This is a probability of error. An example of the use of numerical transmission is for the probe Voyager 1 and Voyager 2. This probe were launched in 1977, so this is a sort of a surprise, because now everyone is familiar with digital transmission, with bit, with internet and so on. But at that time, it was very unfamiliar. The reason is in telecommunication, the problem of transmitting over long distance and avoiding the corruption of the signal was very well known, and also the solutions were very well known. In fact, Voyager was using a digital transmission, and even if nowadays the distance of voyage is huge, is sort of 160 times the Sun-Earth distance, so it's out of the solar system, but very far from the solar system, still these sounds are transmitted signals that are very useful, and they are transmitting imaging. This is very amazing if you say that this image, 600 by 600 pixel, is a technology of 1977. But it's more amazing the fact that even if the power of the signal that you get is 3/1000 times the power of the noise, so noise is 1000 higher than the signal, still it's possible to recover all the bit of the image. So this is done because the duration of the bit is so long that the time bandwidth product increases the signal-to-noise ratio from a very low value up to 15. And when you have a signal-to-noise ratio of 15, now the probability of having a bit error is so small, 10 minus 5, that with a further Reed-Solomon coding, you can put this probability to 0. And this means that the velocity of transmission is 10 bits per second. 10 bits per second is not really a fast transmission, but if you consider the huge distance of this probe from the solar system, they are amazing, the capability to get images from them. Antenna arrays is a very modern and up-to-date technology in which we can use a discrete set of antennas, like this case, this is referred as uniform misplaced linear array, that has the ability to scan the space for looking at different transmission and then estimating the signal emitted by the various sources without introducing interferences. But the good part of this is that in order to estimate the signal from here, here, and here, this is done simultaneously without the need of any mechanical steering of the antenna. How this works? Well, first of all, let us make a model between the emitted electromagnetic signal, that is a sort of transmission, this can be the radio signal, and this is a modulation needed to transmit in the air. This signal comes from the source to the different antenna element with a delay. You see, the signal comes first to this antenna and then to this antenna. So if we write the expression of the signal that is emitted by the source that is in the direction theta m, but it's received by the n element of the antenna, and for every time, this is a transmitted signal plus a delay due to the distance between the source and the single antenna. This distance depends on the source, but depends also on this antenna. And if we write an approximation that we consider this distance as not really the circle, but we approximate this circle by this part of a triangular rectangular, then we can have a very simple expression in which we acknowledge that the signal received by the antenna is the transmitted signal, delayed, the delay is not a problem, but multiplied by this term. And this term, what is this? Well, this term is a complex sinusoid that develop in the direction of the antenna. It means that if we consider the frequency of this sinusoid, that is a spatial frequency, this frequency is one-to-one related to the theta m. Theta m is the angle from which the source arrives. So angle of arrival is matched one-to-one to a frequency of a spatial sinusoid. So it means that if I measure the signal at this array, these are all the elements that makes array, I do a demodulation and do a Fourier transform, each frequency corresponds to a direction of arrival. So I can simultaneously detect and measure the signal at different frequency. It means that I measure the signal transmitted in the different direction of arrival. So to show how this works, I did a simulation in which, in my geometry, I started a different signal that is emitted by the red station that is placed in this position, the blue station, the green station, the dark blue station, and an orange station. All this has a different direction of arrival. This is an array. The array is so small, is placed in this direction, but it's so small that it seems a point to you, but if you draw this in an expanded figure, you see that the array is made effectively by 15 elements. And then what I do? I do the Fourier transform of the array. But first, I do a power spectrum estimate, because a power spectrum estimate tells me for all the frequency, so it means for all the possible direction of arrival where I get some energy. And if you see this power spectrum energy, the blue is in which I don't have any noise, and in the black I consider that I add some noise to the receiver. Well, in any case, you see that are some peak at precise frequency, and this frequency tell where there are most likely transmitter. If you look at this peak, 1, 2, 3, 4, 5, 6, you find here there are 6 major peaks and the other are very, very small. But if you consider 6 major peaks, only 5 correspond to real transmission, and the other is not a peak due to a transmission, but is just a spurious side lobes. So what I can do now, I can do the Fourier transform, and I can compute the signal output of each of the directions that I have estimated. So the Fourier transform I compute only in the frequency corresponding to this emitter, the second emitter, the third emitter. You see also the peak are represented here and the point in the direction of the station. And so let's play the music. First of all, let us play the music input of the single antenna. That is this. Well, you see a terrible mess of everything, because you see all the signal from this station summed together. In addition, you have also noise. Then, let us play the music when I point the array in this direction, that correspond to the first peak, this one. You see that this signal is the correct signal that one possible radio station is emitting. I can also play the second signal. Let me play the third signal. And what happens to the 4? Well, if you consider the 4th signal is this direction. This direction does not correspond to any station at all. In fact, it was not a true lobe, it was a spurious lobe. But how can I tell? When I play this signal, you see the array is not providing a good transmission because it's pointing in a direction where I have no emission. Well, this is a clear example on how can an array scan the space, detect different transmitter and focus it pointing on one transmitter, and this is going very far and has a lot of application in the real world. And this is also the last example of this lesson.